Okay, we're going to carry on with our look at rates of change and motion, but in particular projectile motion. Before we do that, I want to talk about what's called position vectors. Okay, so there's our vector. You recall from when we looked at vectors last year, we could have a position vector, which is x, y, are the coordinates, but we call that a vector, well, I'm calling it u. So OP would be the position vector. XY is the ordered pair or the coordinates, and I could write it as a column vector, so XY there. Now in component form, the horizontal component would be X and the vertical component would be Y. The magnitude of our vector is the length of the vector, so the square root of x squared plus y squared, and the direction the vector is heading in would be the angle it makes with the x-axis, or the positive side of the x-axis, so the inverse tan of y on x. All of that we looked at in our topic of vectors. I'm going to just introduce this new idea of what's called space curves. So all the motion we've looked at so far has been in a straight line. Let's just consider a position vector. So it's going to be a function of time, so scalar t. And so there's our vector. So again, we'll start at O, and it's going off there to P. Now, as time changes, because this is now a function, the vector will change its position, and it will scribe out what's called a space curve. So if I add a little bit, I've just called it delta t. We might end over there at Q. That might be the vector Q. And then I might add a bit more time. This time I called it delta t, and I'll end up with the vector OR. Now, the curve that they travel on is the space curve. So basically it's the endpoints of all the possible vectors. So the velocity vector at any point in time will be a tangent to the curve at that particular point. So at time t, it will be whatever the tangent is at point P. So I've put it there. There's a velocity vector. It's also going to be some function t, because as time changes, then obviously the tangent will change as well. That would be the same for an acceleration vector as well. And the acceleration vector would go in the same direction or the opposite direction, depending on what's happening, as the velocity vector. So to find velocity and acceleration and all their components, vector analysis is what we use. So displacement. So that was my vector r, but I said it was some function, but I could always break it up into a horizontal component and a vertical component. They will both be functions of time as well. Velocity was when we differentiate displacement. So we will differentiate both components of our displacement vector. And remember, with motion, we tend to use the dot notation for the derivative there. So I've written it as x dot times the I plus y dot times the vector j. So the magnitude, well, it is a vector, so it'll just be x dot squared plus y dot squared, and the direction that it travels in will be the inverse tan of y dot on x dot. Acceleration, I'd now go and differentiate velocity. So it's x double dot in the horizontal direction, y double dot in the vertical direction. And the magnitude of the acceleration, again, I could use my Pythagoras distance formula, call it what you will, x double dot squared plus y double dot squared. So let's just look at an example. Here's my velocity function. In the horizontal direction, we've got minus 2 sine 2t, and in the vertical direction, 4 cos 2t. And we're defining time to go between 0 and pi and 2. They've given us an initial condition. So at t equals 0, we have the vector I. So that unit vector in the horizontal direction. Okay, we want to find the position vector. So dx to t we know is minus 2 sine 2t. So if I integrate both of those with respect to time, because to get displacement or position, I would have to integrate velocity. I'm using a definite integral here, and so the initial conditions was that when t equals 0, x was 1. So if I integrate both of those, well, dx goes to x, minus 2 sine 2t is just cos 2t. Sub in, I get x minus 1 is cos 2t minus 1. So I know in the horizontal direction, we have cos 2t. Now let's do the same for the vertical direction. So dy to t is 4 cos 2t. Integrate both of those. This time, when t is 0, we have 0 in the vertical direction. Our initial condition, it was simply horizontal. It was just I. So subbing in for that one, I get the y is 2 times sine 2t, sub in t and 0, and combining it all together, my position vector will be the horizontal component cos 2t times I vector, the unit vector in the horizontal direction, plus 2 sine 2t times the unit vector in the vertical direction. All right. Now this time we've got two different particles, A and B, and there's their equations. Now we want to prove that they will collide when they're travelling at the same speed, but they'll be at right angles to each other. So all we've got to work with is our position vectors. We know they'll collide when they are at the same position, but also at the same time. So let's solve them simultaneously. So the horizontal direction must be the same. T cubed minus 9t plus 8 is 2 minus t squared. I have a cubic to solve, not the easiest thing to solve. Let's have a look at the vertical direction. So t squared is 3t minus 2. That's a little bit easier to solve. I get two possibilities, t equals 1 or t equals 2. Rather than trying to solve the first one, let me just see if one of these works, and then I'll know that's the one we're looking for. So if I sub t equals 1 in, unfortunately I get -1, I don't get 0. So it can't be when t equals 1. Sub t equals 2 in, that works out a bit nicer, I get 0. So I know the time that they meet. It's when t equals 2. Okay, now what are we trying to find? We want to find their speed and show they're the same, but also they're at right angles to each other. Well, when we're talking about direction, we need the velocity vectors because we want to see the direction it's traveling in. So traveling means velocity. So we'll differentiate each of these. So my first one, my A particle, differentiate both the horizontal and the vertical. Now do the same to the B component. Now we said t was 2, so I sub that in. My velocity of the particle A is 3i plus 4j, and in the B it'll be minus 4i plus 3j. Well, let's find the magnitude of each. Yes, A is 5, B is also 5, so yep, they're both travelling at 5 meters per second. What about the direction? Let's use the dot product. If you recall the dot product, if the dot product was equal to 0, then the vectors were at right angles. And yes, this dot product does equal 0. They will collide at right angles to each other as well. Okay, well that was a bit of just about space curves. Let's say we're more interested in projectile motion. This is what we want to look at. We're interested in projectile motion. So far we've just been talking about straight line motion, but projectile motion is not straight line motion. We're going to assume for this that the air resistance is negligible. And in those cases, it really does have little effect on projectile motion. So the only thing that's going to affect it will be gravity. So the acceleration horizontally will be 0. There is no forces acting on it horizontally. Whereas in the vertical direction, gravity is going to have an effect. Now gravity acts towards the ground, so I'm going to make that negative. So negative g for gravity, and we're saying that's in the vertical direction. Some initial conditions. Well, so at t equals 0, we're going to assume it's projected with a velocity of v, and at some angle theta to the horizontal. So let's just draw a little diagram here. So there's my number plane. We're going to start off, we're going off at an angle of theta with a value of v. So there's my initial vector. Now, to work out the initial conditions horizontally and vertically, we can look at the components of this vector v. So horizontally, we get x dot is v cos theta. Vertically, y dot is v sine theta. Now a little bit of time passes, and our projectile is now at this new point. The angle is going to change, of course. It was only projected with theta. Now I'm saying it makes an angle of alpha, but once again we will break that into horizontal and vertical components. Then it could reach at the top there, and vertically it might now be stopping, because once it gets to the top it would stop. And so we would only have a horizontal vector there. And then we would keep going at some point there, but now we're travelling down, so our vector's pointing down. And it'll hit the ground, and it'll make some angle alpha again. Again, I don't know what alpha is, but we would break that up into its components. Now, I'm not saying all of these three alphas are the same. I'm just saying it'll have a different value to what it was projected at. Well, if I was to join all these, we get a parabola. And at each point, those velocity vectors are the tangents to the parabola. But initially, it just makes life so much easier if we start with the origin. So I'm going to assume horizontal and vertical displacement are both zero. Just out of interest, if you want to work out maximum range of a particle, then that'll occur assuming we're projecting from, say, level ground, and it will land on level ground at 45 degrees. Okay, let's find our equations. So we said acceleration in the horizontal direction is 0. I'm calling that dx dot to t. And in the y direction is -10. Let's do the first bit, the horizontal. And again, I'm going to do it via definite integrals. So we'll integrate, v cos theta to x dot. And, integrate dx dot, we get x dot, sub in x dot, sub in v cos. And that ends up being 0. Now, why did I know that was going to be 0 straight away? Because remember, integrate 0, you get a constant. So if I'm going to go constant minus constant, I must end up with an answer of 0. Another advantage, I guess, of using definite integrals. So that right-hand side stays as 0. And we get x dot v cos theta. Let's have a look at y dot. Again, we'll integrate. Well, this time on the right-hand side, we don't have 0, so I'll integrate the t, but that'll become minus 10t on the right-hand side. On the left-hand side, y dot minus v sine theta. Move everything to one side, and there is my velocity in the vertical direction. And so combining that all to get a velocity vector, we'll have whatever the magnitude of v is times cos theta I, and magnitude of v sine theta minus 10t. Okay, let's find displacement. Again, let's integrate. And eventually, there we go, we get vt cos theta. And in the y direction, we end up with vt sine theta minus 5t squared. Now, with all of these equations, well, there's basically 6. We've got 2 for displacement, 2 for velocity, 2 for acceleration. But we should be able to solve any problem that they give us. Some common questions. When does the particle hit the ground? Well, we know that'll happen when y equals 0, so we'll go and solve that equation. What's the range of the particle? Well, once I've found out where it hits the ground, so that's y equals 0, I can substitute into the horizontal component, and that'll tell me where it hits the ground. What's the greatest height? Well, the greatest height will happen when it stops going up. So y dot will equal 0. Solve that particular equation. Once we know when, we can find out where. But this time, I'm going to substitute it into the y component. And the angle it makes when it hits the ground. Okay, again, we'll have to find out when that happens. We'll find the vertical velocity, and we'll use tan theta as y dot and x dot. Now you might be saying, well, hang on, why didn't we substitute into x dot? But remember, that turned out to be a constant, so it's never going to change. So to summarise, what do we know about projectile motion? We know the 2 accelerations. We always start from there. Horizontally, it'll be 0, vertically -g. And the initial conditions, it's okay to quote these, you don't have to derive them every single time, but in the horizontal direction, v cos theta, vertical direction, v sine theta. From there, it's integration to go and find the velocity, go and find the displacement. Now, sometimes in questions, they will give you those formulas to save you some time. So if they do, please don't waste time and derive them. That's why they've given it to you, to save some time. So here's a simple little example. We're going to throw a ball at an angle of whatever the inverse tan of 3/4 is, with a velocity of 25 meters per second. We want to find greatest height. So one of those common questions I was talking about. Well, in order to do that, I'm going to have to find the equation. So my initial conditions, okay. I know it's v cos theta. I've drawn myself up a triangle there because I'm not really interested in what theta is. I'm interested in what cos theta is. So reading off my triangle, cos theta is 4/5. So horizontally we've got 20 meters per second. Vertically, v sine theta will end up with 15 meters per second. So got some initial conditions there. So let's start just like we did before. X double dot is 0. So I want to integrate that. But this time I've got some numbers. So I'm going from 20. That was the initial horizontal velocity. And if we integrate that, we end up with that the horizontal velocity is a constant 20. Now, in the vertical direction, integrating that one, we end up in the vertical direction, we get 15 minus 10t. So gravity is having an effect of the vertical direction. Okay, let's find displacement. Integrate again. 20t for displacement in the horizontal direction, 15t minus 5t squared in the vertical direction. We've got all the equations. We can now go and solve any question that they want. Remember, they ask for greatest height. That's going to happen when it stops going up. So the vertical velocity is 0. 1.5 seconds, so 3 on 2. Sub that into the vertical displacement, and we get 45 on 4. So we know that the highest it is above the ground is 11.25 meters. What's its range? Look, I don't have to work out the time of flight because I know a parabola is symmetric. And because we're landing on the ground and we're projected from the ground, if it took 1.5 seconds to go up, it'll take 1.5 seconds to go down. So the time of flight is 3 seconds. Now, if you didn't realize that, then of course you could go and solve y equals 0. Sub in to find the x value and we get 60. So our range is 60 meters. Well, after half a second, what direction is our ball traveling in and how fast? So we need the two components of velocity. So when t equals half, well, horizontal velocity doesn't change, so we know it's 20. Vertical velocity is 10 in the positive direction. So that tells me this particle is going up. Makes sense. We said it reaches the greatest height after 1.5 seconds. Let me just draw myself a triangle there, or a vector diagram if you like, to resolve these. Horizontally 20, vertically 10, we're going up. Bit of Pythagoras. We know the magnitude of that vector is 10 root 5. A bit of trig, and that angle would be 26 degrees 34. After half a second, we know we're traveling at 10 root 5, making an angle of 26 degrees 34 to the horizontal. All right, well, that was quite a bit of theory to start the term off with, but 10A is our first look at projectile motion.